Hello friends, today's video is all about bioinstruction series of crystallization of a melt. But before going to bioinstruction series, I would like to put some questions before you. So the questions are: why hydrothermal deposits form towards the end of the crystallization? The structure of melt at different pressure and temperature? Why the silicate structure changes with progressive crystallization? How aluminum in quartz is useful, and why quartz is used as a pyro and piezoelectric metal more often? So this is a bioinstruction series. The left side is the discontinuous one and the right side is the continuous one. And towards the end of the crystallization, we have orthoclase, muscovite, quartz, and zeolite, and some hydrothermal deposits. So the first mineral to crystallize from the bioinstruction series is phosphorite, having a composition of Mg to SiO4. And this is the structure of one silicon tetrahedral having a net charge of -4. So what happens when olivine crystallizes at higher degree temperature? That two Mg ion just make bond with two oxygen atom of the silicon tetrahedral, and we all know that the charge of 1 Mg is +2, so 2 Mg, that means +4, and +4 -4 cancel, and that's why we have a net negative, we have a net charge of 0 in the olivine. And that's why when we do the EPMA analysis of a phosphorite, according to the weight percent, there we can see that there is one MgO, that is the second MgO, and there is one SiO2, and that's why we get the weight percentage according to the structure. But what happens after the crystallization of olivine? We know that at some temperature we have peritectic reaction, and olivine reacts with silicate melt to form enstatate. But the main question is that how a SiO2 melt, because SiO2 melt have a net charge 0, because Si has a charge of +4 and O2 has a charge of -4, so +4 -4 cancel each other, and we have a net charge of 0, reacts with phosphorite to form enstatate. So what happens is that in place of silica in the silicate structure, we have some amount of substitution of aluminum. I have written this. In place of one Si4, I have substituted one aluminum +3. But till now, there is not, this is not balanced, because silicon has a charge of +4 and aluminum has a charge of +3. So there is still one charge disbalance in this equation. So what happens actually is that in place of one Si4 plus, we have one Al +3 and one H plus substitution in the silicate melt. And as the temperature decreases, the bonded H plus in the silicate melt just get removed, and due to the removal of the H plus ion, there is a net negative charge in the silicate melt structure, and due to that net negative charge in the silicate melt structure, it reacts with the previously formed olivine or phosphorate to form enstatate. And I have written the same thing in the bracket, that SiO2 melt, and I have removed one H plus ion, and I have the same composition of the melt SiO2 but with a net negative charge. Due to the net negative charge, the melt reacts with the phosphorate to form enstatate. But what happens to the H plus ion that is removed from the older melt? The removed H plus just make bond with the oxygen atom of the newer melt. Why I am using the term newer melt is that due to crystallization, the composition of the melt also changes. So the H plus that is removed from the older melt is now make bond with the O, that is oxygen atom of the newer melt, and make another anion, that is the hydroxyl anion, that is OH. So this I have written, the removed H plus make bond with the newer melt. As more and more H plus remove and bond with the newly evolved melt, the melt becomes more hydrous rich, and as a result the OH minus ion forms. And we know that as we go down in the bioinstruction series, the temperature also decreases. So at higher temperature, OH minus cannot form in the melt, but in the lower temperature, OH minus ion can form in the melt. So the H that come from the newer melt, and it happens due to the crystallization of enstatate. Okay, so the addition of OH minus ion with changed magma composition crystallizes amphibole and biotite. The larger sites between the silicate structure are compatible with the charge and shape of OH minus ion. This stage of crystallizations form phyllosilicate and double chain inosilicate structure. Okay, so we have bigger sites in between the silicate structure in case of amphibole and biotite, and due to the evolved magmatic composition and the OH minus ion in the magma, we have amphibole and biotite crystallization at this stage of Bowen's reaction series. So as the crystallization of OH bearing phases happens, there is again depletion of H2O in the melt. But on the other hand, we have also crystallizing anorthite and albite to orthoclase. Okay, so what happens when we are crystallizing anorthite and albite? The same phenomena that we have discussed in olivine, that as the melt try to react with the cations, it tries to remove the H plus from the older melt, and the H plus ion just get accumulated in the newer melt. So that I have written that the silicate structure Si4O8 that we generally found in plagioclase, that is the tectosilicate structure, because the ratio is 1:2, is not able to form a plagioclase until some aluminum is substituted, because the charge is zero, so it cannot react with any kind of cation. Okay, although the structure is a tectosilicate structure, but due to the lack of charge, it cannot form a plagioclase. So what happens actually is that there is some amount of aluminum substitution in the silicate structure, and if you will calculate the charge of Al2 Si2O8, you will get -2 charge, and due to this net negative charge, the calcium ion, because calcium has a charge of +2, so calcium ion make bond with the aluminum silicate structure. So there is a similar kind of substitution. Si4 plus is equal to Al plus 3 plus H plus in the silicate structure. And as the temperature decreases, the melt becomes rich in OH minus ion, but as the series is a continuous series, it is unable to form any kind of hydrous bearing phase. So first we have non-hydrous mineral, that is olivine and statite, and after that we have hydrous mineral, that is amphibole and biotite, and again we have some anhydrous mineral like orthoclase, and again we have some hydrous mineral like moscovite. So what happens is that after the crystallization of moscovite, the OH minus ion in the melt again increases. So the newer melt having a composition of having a felsic composition, and some potassium and aluminum, and with some silica and with some hydroxyl ion, moscovite is the suitable mineral to crystallize from the melt. So this is the main reason why there is first anhydrous mineral crystallization, and then there is hydrous mineral crystallization, then there is again anhydrous mineral crystallization, that is orthoclase, then again there is hydrous mineral crystallization, that is moscovite. So after the crystallization of moscovite, as the temperature decreases and now most of the cations have formed the complex minerals in the Bion series, very little amount of cations left in the melt, and the melt, that is the silicate melt, it itself crystallized in the form of quartz. So after moscovite, what happens, when there is a lack of any type of other cations, quartz, that is SiO2 structure, SiO2 that is SiO2 silicate structure, directly crystallize in the lower temperature. Okay, so after the crystallization of quartz, what happens, only it is left, the crystallization of quartz left only a water bearing solution with some cations dissolved in it, and this is the hydrothermal deposit that we see in nature. So the hydrothermal deposit, the I mean the basic of the hydrothermal deposit is that the H plus ion just jumps from the older melt to newer melt, and after the crystallization of quartz, when there is no silicate left in the melt, only some amount of water and dissolved cations left in that high temperature and high temperature water bearing solution, it forms hydrothermal type of deposit. But it is also seen that, as a matter of surprise, it is also seen that even quartz that crystallize from the final silicate melt have some trace amount of aluminum present in its structure, which also concludes that the structure of SiO2 has some amount of H plus cation. Okay, the presence of H plus cation is the key factor to the piezoelectric and pyroelectric property of the quartz. And the aluminum in this quartz, I have written here the silicate structure. This is not silicate structure. The aluminum in quartz is mainly pressure sensitive, and hence it is used as a barometer or to measure the pressure of formation of that quartz, because quartz occur in variety of situation in metamorphic rocks and igneous rocks. So in order to calculate the pressure, must need need the we must need to calculate the aluminum values in the quartz, as it is pressure sensitive in quartz. So this is all about the Bowen's reaction series, and I hope that the questions that we have discussed in the during the questions that we have discussed, the 5 questions, I think you'll get the answers. So if you have any kind of doubts or queries, you can mention in the comment box, and I will try my best to answer those questions. Thank you.